Chapter 2, Exercise 27. Hint. Use the given hint. Solution. By example 22 and example 23, the Euclidean space Rk has a countable base set Vn. Define the index set I equaling this, and let W equal this. Assume that P element of P intersection W. Then there exists an index n such that P element of Vn and E intersection Vn is at most countable. Since Vn is open, there exists delta greater than 0 such that this. However, since P is a condensation point of E, the set here is uncountable. But this contradicts the assumption that E intersection Vn is at most countable, since this. See Theorem 2.8. Thus, this and that. To prove the converse inclusion, consider a point P element of W complement and its neighborhood here for some delta greater than 0. Since this is open and this is a base for Vk, there exists some n such that this. If n element of I, then P element of W, which contradicts our assumption that P element of W complement. Thus, n not element of I, meaning that E intersection Vn is uncountable, and consequently, this is uncountable as well. Since every neighborhood of P contains uncountably many points of E, we conclude that P element of P. This proves the equality P equals W complement. Since W is a union of open sets Vn with n element of I, it follows that W is open, Theorem 224a, and hence P equals W complement is closed. The set here is at most countable, as it is a countable union of at most countable sets. See corollary to Theorem 212. Now, let P element of P and delta greater than 0. The set here is countable, while the set E intersection W is at most countable. By Theorem 2.8, we have that this is at most countable since this. From the corollary to Theorem 212 and this, we conclude that the set here is uncountable. Since this, it follows that the set here is uncountable and therefore infinite by Theorem 2.8. This implies that P element of P prime and thus P is perfect. We have shown that this is at most countable, meaning that at most countably many points of E are not in P. Comments. This proof only uses the separability of Rk, so the result remains true in any separable metric space. If a metric space X is separable, E is subset of X, and P is the set of all condensation points of E, then P is perfect, and E intersection P complement is at most countable. Thanks for watching.